right, in 6.2, we are still looking at a standard normal distribution. And notice what it says. It is not sufficient to only know the difference between an x value and the mean. We need to also consider the spread of the curve, or the standard deviation. What we really want to know is the number of standard deviations between the measurement and the mean. This distance takes both mu and sigma into account. So I'm going to pull up the last example we were looking at in 6.1. So in this case we looked at and we were comparing, and we had their means and their standard deviations, and we were trying to see who did better. But based upon our pictures, we can't say with certainty who did better on the test, and that's difficult to do. We need to know exactly how many standard deviations away from the mean that it is. We know it's between 1 and 2, but we need a more exact value. So what we do in this case then is we standardize our data value. So you all have taken standardized tests before. So in this example, Doug's score is a 57, Jennifer's is a 1-2. These are raw scores, or x values. So these are their actual scores. What we need to do is standardize these values so we can do a direct comparison. So what occurs when we standardize a data value is it tells us how many standard deviations away from mu that we are. So this is what we're looking for, exactly how many standard deviations away from mu. So what we're going to be doing, and this is some terminology you need to be familiar with, is we're going to take a raw score. A raw score is also known as an x value, and we're going to standardize it, and that standardized value is known as a z value. So here's the formula that we're going to use. So what we're doing here is we're taking a raw or an x value, and we are converting it into a z, or a standardized value. Now, when we do this calculation, always round to 2 decimal places. So I'm going to take this formula and I'm going to go back to Doug and Jennifer, and I'm going to standardize their values. I'm going to find out exactly how many standard deviations away from mu that they are, so then I can see if I can tell who did better on their test. So to standardize the value, we're going to look at Doug first. So to standardize, it would be x, which is 57, minus mu, which is 50, divided by 5, and remember, put this in parentheses. So if we do that, I have not done that calculation yet, so 57 minus 50 divided by 5, I get 1.4. Since we go to 2 decimal places, I'm just going to put 1.40. So this right here tells me that Doug is 1 full standard deviation and 0.4 away from the mean. So his raw score is 57, but his standardized score is 1.4. So in essence, get that a little closer. So in essence, the 1.4 and the 57 are the exact same score. It's just one is raw and one is standardized. So now we're going to do that same thing with Jennifer. I'm going to standardize her score, so it would be x, which is 120, minus mu, which is 100, divided by sigma, which is 15. So I go to my calculator, and I get 1.3333 going on forever, normal rounding rules, that would be 1.33. So this tells me that Jennifer is 1 full and then 0.333 standard deviations away. So hers would look like this. So now I can do a direct comparison. Here's average. The further away from the mean you get going to the right, the better you did on the test. So Doug is slightly, just a little bit further away from the mean than Jennifer is. So Doug actually did a little bit better on his test than Jennifer did on hers. And that's why we use and we standardize values. Now, before we get to this, I want to come down here and just draw a curve, because remember, this is still a normal curve, it's just now that we have standardized it. So here's what that would look like. We still have our normal curve. So now, instead of putting mu here, I know when it's standardized, mu is always 0. And then as I go to the right, 3 standard deviations, my standard deviation is 1, so I do 0 plus 1, plus 1, plus 1. And as I go to the left, I will subtract 1. So it looks like a number line. Now, since this is a normal curve, then I know that this is still 34%, 13.5%, 2.35%, and then of course the tail is 0.15%. And then it's symmetrical, so those same percentages are on the left. So the only difference is the horizontal line. Previously, when we were given mu, we put it here, but now when we standardize, that will always be 0. All right, so now let's go back up here. And it says, what does a standard z-value tell us? Okay, remember a z-value tells you how many standard deviations away from the mean that you are. So a standard z-score close to 0 tells us that the measurement is close to the mean, because recall that cuts it in the half is mu, so anything close to 0 tells me I did close to average. A positive standard z-score, so everything positive goes to the right, that means that I have done above average. Any negative z-score, which is to the left of mu, tells me that I did below average. Now, a rare or unusual occurrence is any value outside the range of 3 standard deviations. So here and here, that is not going to occur very often. So let's take that information. So the only difference from 6.1 that we're now doing in 6.2 is we are standardizing or looking at standardizing our values. So let me just write this over here. X values are raw scores, because you're going to see that terminology. So anytime you see the word raw, you know you have an X value. Z values are standardized. Can I get it all in there? Barely. Standardized. All right, so a normal distribution has mu of 17 and sigma of 3. Now, this is not asking me to draw the picture, but I know some of you guys are more visual learners, so I'm going to go ahead and do this. Now, these values, when they give me mu, if I put 17 down here, 17 is an X value, okay? It's a raw score. So as I draw this and I add 3, and as I subtract 3, these, if I write these values here, each of these are X values. These are all raw scores. Now what it's asking me to do then is says, find the z-score when X is equal to 21. All right, well let me get an idea of this. If I come over here, here's 20, 21, so I should get a z-score that is 1 point something because it's between 1 and 2 standard deviations away. So we would have, and use our formula, so we will have 21 minus 17 divided by 3. I don't have that calculated, so I'm going to do that. And it's 1.33, which makes sense. Find the z-score when X equals 12. All right, well here's 17. 12 is below average, so right there it tells me my z-score, because remember, your z-values, this would be 0, 1, 2, 3, this would be -1, -2, -3. So 12 would be below average. That tells me that I'm going to have a negative z-value, and 12 falls between -1 and -2. So I should get a value between -1 and -2. So we would have 12 minus 17 divided by 3. And I get -1.666666, so I'm going to round to 2 decimal places. Normal rounding rules, so -1.67. So that makes sense in relationship to my drawing. Find the z-score when x is equal to 17. Well, here's 17. That's an x value. What is the standardized value? Well, if I plug everything into the formula correctly, I should get 0. X, 17 minus mu, 17, divided by 3. Well, 17 minus 17 is 0. 0 divided by 3 is 0. So that makes sense in relationship to my picture. So this is when we were given the raw. So we were, for all of these examples, we were given the raw score, and we were asked to calculate the standardized. So that's one way you will do it. Okay. A pizza parlor franchise specifies the average amount of cheese on a large pizza should be 8 ounces and the standard deviation 0.5. An inspector picks out a large pizza at random and finds that it is made with 6.9 ounces of cheese. Assume the amount of cheese on the pizza follows a normal distribution. If the amount is below the mean by more than 3 standard deviations, the parlor will be in danger of losing its franchise. Well, my guess is it's not selling very many pizzas if it's being that stingy on their cheese. But let's take a look at this. Okay, information that is given. It tells me that the average amount of cheese is 8 ounces. Okay, so the average is 8 ounces. So that tells me mu equals 8 ounces. Standard deviation is 0.5. So what an inspector does is he picks out a large pizza at random and finds that particular pizza has 6.9 ounces. So that's a raw score, or an X value of 6.9. All right, so there's the information we have. So draw the distribution. All right, it's a normal curve. Here's 8 ounces. So this would be 8.5, 9, 9.5. Everybody's hoping to have above average with their pizza, the cheese. All right, so this would be 7.5, 7, and 6.5. So remember, it's out here. If they are below 1, 2, 3 standard deviations, then they might lose their franchise. Now, if we standardize these numbers, then this is what we're looking at. All right, so part B says how many standard deviations from the mean is 6.9? Well, if I just look at my picture, 6.9 is going to be somewhere around here. So if it asks me how many standard deviations away, well, what tells me standard deviations? This is asking me to find the z value. So we're going to calculate z, which I can tell it should be between -2 and -3 standard deviations away. So x is 6.9 minus mu is 8 divided by 0.5. And we get -2.2. I'm going to go ahead and put -2.20. So that makes sense. negative 2.20. So that's how many standard deviations away that we are. All right, it says, is the parlor in danger of losing its franchise? Well, it said it was in danger if it was below more than 3 standard deviations. Well, here's 1, 2, 3. It's not below. So is it in danger? No. Why or why not? Because it's not below 3 standard deviations, which means to be below, you would have needed to get negative 3 point something, and it would have been smaller or less than 6.5 ounces of cheese. Although they're kind of getting close there, so I would be a little concerned. Okay, so these are 2 examples of when we're given the X value, we're given the raw, and we calculated the standardized number, or the Z value. So now we're going to look at doing that the other way. So now we're going to be given the standardized, and we want to then find the raw. So that's this formula here. So this is when you are given, so in this is when you are given the Z value, and you are going to calculate the X value. You're given the standardized, it wants you to calculate the raw. We use this formula here. All right, so a normal distribution has mu of 48 and sigma of 7. Now again, if it doesn't ask you to, you don't have to draw the picture. I'm just going to continue to do so for my visual learners. So mu is 48. As I go to the right, I add 7. So 55, 62, 69. As I go to the left, I'm going to subtract 7. So 41, 34, and 27. Now those are raw scores. If I looked at my standardized, it would look like this. All right, find the raw score. All right, when you see this wording right here, you know it's asking you to find the X value. So we know that we are negative 1.6, so we are below average. We are between negative 1 and negative 2, so we should calculate a number between 34 and 41. So I'm going to apply this formula here. Negative 1.6 times sigma 7 plus mu is 48. Plug that into your calculator and you get 36.8. So sure enough, that was between 34 and 41. Find the raw score, find the X value when Z is equal to 0. Well, here is Z is equal to 0, so we better calculate 48. So it would be 0 times 7 plus 48. Well, that makes sense because 0 times 7 is 0 plus 48. That gives you your 48. Find the raw score when Z is 0.75. So it's a positive Z, so we know we're above average, and 0.75 is between 0 and 1, so we should calculate a number between 48 and 55. So 0.75 times 7 plus 48 is equal to 53.25. And sure enough, we calculated a number between 48 and 55. All right, moving on. Rod figures it takes an average of 17 minutes with a standard deviation of 3 minutes to drive from home, park his car, and walk to class. And it's not written, but it needs to say it's a normal distribution. So I'm going to add that. Okay? All right. So it says an average of 17 minutes and a standard deviation of 3. So I'm going to draw my curve. So I'm going to add 3, 20, 23, 26. And then I'm going to subtract 3, 14, 11, 8. All right, part B. One day it took Rod 21 minutes to get to class. Is the z value positive or negative? Well, here's my z values, 0, 1, 2, 3, negative 1, negative 2, negative 3. 21 minutes would be about right here. That's where about 21 minutes would be. So it is to the right of mu, so that would tell me that my z value is positive. Then it wants to know exactly how many standard deviations away that it is. Well, I know it's between 1 and 2, but we're going to go ahead and calculate that. So that would be x, 21, minus mu, 17, divided by 3. And it is 1.33. What commuting time? Now, commuting time is an actual time, so this means this is saying what raw score, because a raw score is a real life value. Commuting time is real life. So when it says what commuting time, it's asking you to find the x value that corresponds to a standard score of negative 2.5. Now this tells me how many standard deviations away that we are. So here's negative 1, negative 2. So it would be about right here. So we know it should be between 8 and 11 minutes. So I'm just going to use that formula. X equals negative 2.5 times times sigma plus mu. And that gives me 9.5 minutes. Now, can Rod count on making it to class in this amount of time or less? So, if I shaded that amount of time or less, that's the likelihood that he would make it to class on time. Does not appear to be very likely. So can he count on making it in that time or less? No. I would not count on that at all. All right. All right, so we've been looking a lot at normal curves and their probabilities. And we know that the area under this curve is 1, and that these represent proportions, which is the same thing as a percentage or area or probabilities. Now, what we have done so far and what we have learned is if I shaded all of this, you would tell me that I have 50% of the area shaded, or the probability is 0.5. But what if I did this and I added this additional amount? Based upon what we've done so far, could you tell me the area that is shaded? Now, you would say, well, this is 50%. From here to here is 34%, but I'm not 100% sure how much you have shaded in, so I could give you an idea, but it wouldn't be exact. Well, we're going to learn how to find that area exact now. And this is by using the standard normal distribution table. Now, this is in your ebook in the reference pages in the tables. And it's table 5. It's appendix 22 and, sorry, I don't need that one, 22 and 23. Now, if you'll notice, this says we use a left-tailed z-table. So these two pages are called z-tables, and here's why it's left-tailed. Because these are your probabilities, and your z-values are here, and to this z-value, these probabilities are the area that lies to the left. So you'll notice we have what's called a negative z-value, and then the other one, it's left-tailed as well. Here are our positive z-values. So we're first going to learn how to use the table. All right, so this first example, it says use the standard normal table or the z-table to find the given areas or probabilities. So the area that lies to the left of. Now, while we're learning this, I am going to draw the pictures. So I have positive 2.17. All right, so here's 0, 1, 2, 3. So 2.17 would be approximately right here. And it tells me, it wants to know the area to the left. So it wants to know this area. Now, I can tell you how much is here. There's 50% plus 34% plus 13.5%. But I don't know how much is in this little bit. Now, what the table is going to tell us, because we have a left-tailed table, it's going to give me the area that lies to the left of this value. So what I'm going to do is I'm going to go to the positive z-table. So look in the column to where you have your positive numbers. Here you have the whole number and the number that is in the tenths place. And then up here you look for the number that is in the hundredths place. So we have 2.17. So I'm going to go to 2.1, which is here. And then at the top, in the hundredths place, I have 7. So I'm going to come down. And so, oops, you can't see it, sorry. It gives me 0.9850. So this area is 0.9850. Oops, sorry. Now, since it did ask for area, I'm going to give that as a percentage. So I move my decimal point 2 places. It would be 98.5%. All right, if you hear music in the background, there's a class next door to me that is playing some music. So I don't know if you can hear that or not, but it's very loud. Okay, moving on. Now, this is a probability, so I'm going to leave my answers a decimal, and what you want to watch for is the inequality. So I'm going to locate negative 1.20. Okay, negative 1.20 and less than tells me to shade all the numbers that are smaller than. So I'm shading to the left, and I know I have a left-tailed table. So I know when I go to the table, it'll give me the area that lies to the left, okay? Well, actually, it'll give me the probability. So now that we're doing probability, I'm going to leave my answer as a decimal. So the probability that z is less than negative 1.20. So I'm going to go to the negative z table now. And in this column, I'm going to look for negative 1.2. Which is right here. And then in the hundredths place, we have 0. So it's that first column. And the area is 0.1151. So the area that lies to the left, or the probability, is 0.1151. So since it's a probability, I'm going to leave my answer as a decimal. Now, we have a left-tailed table. Both of these examples We're shading to the left, so all we had to do is locate the z value on the table and just read the value off of the table. Now, what happens is we don't always shade to the left. So we have to look at what happens when we shade in a different direction. So now this says, what is the area to the right of z equals 0.43? All right, so 0.43 would be approximately here. But it tells me to shade to the right. But we only have, and we only use a left-tailed table, which means when I go to the table, it's going to tell me the amount that goes to the left. So now it's going to give me, in this particular example, the non-shaded. So I'm looking for 0.43, so I get 0.6664. And since we're dealing with area, that would be 66.64%. All right, but I need the shaded. And what we've been given is the non-shaded. Well, this is where you need to remember that the area under the curve is 100%. So to find the area, we do 100%, the full curve, minus the non-shaded, 66.64%, to find the area that is shaded. .36%. So this is your shaded area. Now, here's what that looks like as a probability. Now, one thing I want to point out, notice that this one, the last one was just a less than. Now, this inequality has changed. It's a greater than, but now it shows greater than or equal. When we're dealing with the table and probabilities, you will get the same answer if this was greater than or equal. We don't distinguish or get a different answer whether that additional or equal to is there or not. So now I have negative -1.07 and since this is the inequality greater than, then I know I'm shading to the right. Well, again, our table gives us the probability or the area to the left. So when I go to -1.07, so here's -1.0, and at the top I'm going to look for 7 in the hundredths place, and I get 0.1423. So as a probability, I'm not going to change these two percentages because that's area, but as a probability, then the area underneath, I convert 100% to just 1. So I do 1 minus 0.1423. .8577. So now what you have to remember is anytime the shading is to the right, you always do either 100% or 1 minus the number from the table. All right, there's one more scenario that can occur. Whoops, going the wrong way. And this is when you're shading between two values. All right, both of these are positive. So we have 0.56. And we have 2.1. and my shading is in between. But again, our table is just left-tailed. So when I go to find the value or the probability to the left of 0.56, it's going to give me this non-shaded portion here. When I go to find the probability to the left of 2.1, it's going to give me that lies to the left, which will include this shaded portion and this non-shaded. So what we have to do here, well, let's find those values first. Okay, 0.56, 0.56, 0.7123, and then 2.10, 0.9821, so to find the area that is shaded, you're going to subtract these two values. And let's see, we're doing area, so 71.23%, 98.21%. So the area will be, and you always take the larger 98.21% minus the smaller value, 71.23%, and you get 26.98%. Now you always take the larger, or the one further to the right, the larger minus the smaller, because what would happen if we would switch those? If we put 71.23% minus 98.21%, we would get a negative value. And remember, area and probability cannot be a negative value. All right, so what does that look like as a probability instead of area? So we have a z value between two numbers. So we have a positive and we have a negative. So we have negative 2.14 and we have 1.76. And we want to know the area that is in between them. And we know that our table is left-tailed. Let's see, negative 2.14, negative 2.1, 4, 0.0162, and then I have 1.7, 1.76, 0.9608. And since this is probability, I'm going to leave my values as decimals. So I use the larger 0.9608 minus 0.0162. So that probability is 0.9446. And that makes sense. I have most of this shaded in. So be sure your answer makes sense. Here, it wouldn't make sense to get a number over half. I have well less than half shaded in, so be careful of that. Okay, so a summary on the z-table. Z-table we will be using a lot of, so you need to get very familiar to where you can use the z-table. Otherwise, your life might be a little miserable here for a while. So anytime that we are finding the area to the left or a probability to the left, so just a rough draft, this is when we have something to the left. So it would be left, the inequality would be less than. Then to find the area of the probability, you just use the number from the table. Use the table value. All right, anytime that we are, let me do this too, that was a less than. Anytime we are shading to the right, which is a greater than, so one of many examples of what that could look like is this. Then anytime it goes to the right, you know you have to take 1 minus the number from the table. And then the last example was when it was shaded in between. So that could be something like this. So to find the area between the two z values, or the probability between two z values, look up both table values, and you're going to take the larger minus the smaller. Now, something that can occur, doesn't happen very often, but it might, and that is, what do you do if your z value is not on the table? So here's what I'm saying before I go over these. Say that I want to know the probability that z is less than negative 4.10. Well, here's -1, -2, -3. So, goodness, to get to -4, it would be somewhere way out here, and it wants to shade to the left. So it wants to know that teeny tiny area. So I'm going to go to my table. So I'm going to go to the negative z table, and I'm going to look for -4.10. Well, I go, here's -3, -4, it looks like, or I'm sorry, -3.49 is the smallest number. So what do? Well, this is where you need to look at the small print at the bottom of the table. For values of z less than -3.49, use 0 to approximate the area. So since I'm less than, I just use the number from the table, and it is telling me to use 0. And that's because it's so small, it's just so insignificant. There's eventually a number out here. It just is so small that we just use 0. So that's why this says, look closely at the bottom of the standard normal table. And on the negative z table, which we just looked at, we use 0 if we were on the positive side. So if I was doing the probability that z is less than positive 4.10, here's what that would look like. It would be way out here, and then if I'm shading it's less than to the left, it would be shading all of this, and it says use 1. So in essence, we have the whole thing shaded in. So just be aware that doesn't happen a lot, but it could happen. All right, that completes 6.2.